Water reservoirs around the world are being harmed by acid deposition. Acid deposition to aquatic environments gradually increases concentrations of strong and weak acids, lowering pH. Changes of 1 unit in pH can alter aquatic ecosystems by killing some organisms and harming others. To study the effects of acids on aquatic organisms, biologists prepare solutions of known concentration by a laboratory procedure known as serial dilution. To demonstrate the techniques of serial dilution and the effects of dilution, we will use a 1.0 mole per liter colored solution. The serial dilution begins by extracting 10 milliliters of the original solution using a 10.0 milliliter volumetric pipette and a bulb. Pay special attention to the technique required to use the bulb and pipette. Notice that the tip of the pipette touches the side of the waste beaker as the liquid level drops. An exact volume is obtained when the bottom of the meniscus reaches the calibration line. The 10.0 milliliters are transferred to a new volumetric flask. Deionized water is added to dilute the original solution. A wash bottle is used to finish filling the volumetric flask up to the 100 milliliter calibration line. Accuracy is important. At eye level, the bottom of the meniscus must be even with the calibration line. The volumetric flask is stoppered and the solution mixed to ensure an even concentration of chemicals within the solution. The first dilution yields a solution 1/10 as concentrated as the original. Since 1/10 of the original solution is now in 10 times the volume of solvent, the concentration of the diluted solution will be 1/10 of the original. The second dilution begins by pipetting 10.0 milliliters of the solution prepared in the first dilution. The 10.0 milliliters of diluted solution are added to a volumetric flask. It is topped up to the 100 milliliter calibration line with deionized water. The second dilution yields a solution 1/100th as concentrated as the original. Again, we see a decrease in the color intensity. A third dilution produces a solution with 1/1000th the concentration of the original solution. The intensity of the color of solution decreases with each tenfold dilution. Now let's return to the problem of an aquatic ecosystem threatened by acid deposition. A healthy lake has a pH of 6. To create solutions of pH 6 and lower for studies, biologists can dilute a strong acid of known concentration. Hydrochloric acid is a strong acid. 10 milliliters of 1.0 mole per liter hydrochloric acid are added to a volumetric flask using a volumetric pipette. Hydrochloric acid ionizes completely in water. Therefore, the concentration of the hydronium ion being added to the volumetric flask is equal to 1.0 mole per liter. Deionized water is added to fill the flask exactly to the 100 milliliter calibration line. The change in concentration is inversely proportional to the change in the solution's volume. If water is added to the 10 milliliters of 1.0 mole per liter hydrochloric acid in the flask until the final volume is 100 milliliters, the volume has increased 10 times and the concentration becomes 1/10 of its original. The concentration of the strong acid, and therefore the concentration of the hydronium ions, is 1.0 times 10 to the negative 1 mole per liter. The pH should be 1.00. The solution is poured into a beaker. The pH is measured and found to be 1.04. A second, a third, and a fourth dilution are performed, and in each case the pH is measured. The concentration of hydronium ions after the second dilution is 0.010 mole per liter. The pH meter reads 2.09. The concentration of hydronium ions after the third dilution is 0.0010 mole per liter, and the measured pH is 3.15. The concentration after the fourth dilution is 0.00010 mole per liter, and the measured pH is 4.09. These solutions can now be used in biological tests. Biologists are also interested in the effects of weak acids. The third demonstration is the serial dilution of 1.0 mole per liter ethanoic acid, a weak acid. 10.0 milliliters of 1.0 mole per liter ethanoic acid are transferred to a volumetric flask using a volumetric pipette. Again, deionized water is added from a wash bottle and used to fill the flask exactly to the 100 milliliter calibration line. The concentration of the weak ethanoic acid solution is now 0.10 mole per liter. The solution is poured into a beaker. The pH is measured and found to be 2.90. Are you surprised? Weak acids do not ionize completely. A solution of 0.10 mole per liter ethanoic acid is only 1.3% ionized. The concentration of hydronium ion in a 0.10 mole per liter solution is 1.3 times 10 to the negative 3 mole per liter. A second, a third, and a fourth dilution are performed, and in each case the pH is measured. After the second dilution, the concentration of the ethanoic acid solution is 0.010 mole per liter. 0.010 mole per liter ethanoic acid is 4.2% ionized. The concentration of hydronium ions in the solution is 4.2 times 10 to the negative 4 mole per liter. The measured pH is 3.39. 0.0010 mole per liter ethanoic acid is 13.0% ionized, and the hydronium ion concentration is 1.3 times 10 to the negative 4 mole per liter. The measured pH is 3.88. 0.00010 mole per liter ethanoic acid is 42.4% ionized, and the hydronium ion concentration is 4.2 times 10 to the negative 5 mole per liter. The measured pH is 4.40. These solutions can now be used in biological tests. After each serial dilution, both the strong acid and the weak acid solutions have the same concentration. For each dilution, the weak acid has a lower hydronium ion concentration and a higher pH compared to the strong acid. This is because only a fraction of the weak acid actually ionizes to form hydronium ions. Knowing that the percentage ionization of strong acids is 100%, and that the percentage ionization increases for weak acids with dilution, helps biologists make predictions about the effect of acid concentration on aquatic organisms.